Hey guys, it's me, Felipe, one of your fellow classmates, and I'm making this video because I thought I would share with some of you some interesting insights, and hopefully maybe if you get another view of the lecture, it could provide you with a different perspective that could help your intuition. I say that because I know I have a really hard time with all this stuff. I know some folks think that I'm writing mad, and it's like I must no, I'm writing mad because I'm really, really bad. That's just how much I have to do just to catch up. But I know sometimes getting a different perspective can be very helpful. So I wanted to see if I could complement Dr. Ghamsary's lecture by showing you how I see it. Now, it's likely that I'm going to make some mistakes here, so I'm going to send this to Dr. Ghamsary, and if whatever, or not if, I'm sure that whatever mistakes I make, I will update the video, and hopefully, they won't be too bad. Now, you might be wondering, well, if I'm going to make all these mistakes, then why should I even bother watching? Well, like I said, the real point here isn't so much the accuracy, although I'm trying to be very, very accurate. The real point is that if you see it from a different perspective, see it the way somebody else sees it, that could sometimes give you a second angle, and that could aid in your own intuition, because this stuff, I would not recommend memorizing it. This is just horrible trying to memorize it. I don't care if you write it on the paper, it's just not going to work. Getting the intuition is far better, and I think the way I see it, I think I've got it. It took me a while, so anyway, let's begin. Okay, so first, I'm going to go ahead and type up the data, and we can go ahead and test it. This is for the first part, just making sure that everything is here. Person, systolic blood pressure, the QET, the age, then your smoking status, okay, which is of course 1 if you're a smoker and 0 otherwise, and race, okay. So our data input is no problems. So we move into the next one, which is we're going to go ahead and do a couple of plots. Okay. And so let's go ahead and check them. Now here, of course, we're going to go ahead and we run the t-test. And the t-test just gives us the mean values. Of course, you know this already. This is the mean value. This is the mean blood pressure of non-smokers. Here, let me make it bigger. Mean blood pressure of non-smokers and the mean pressure of smokers. There's the difference. Okay. Now, we're going to go ahead and check further. You know all these features, so I'm not going to spend too much time checking for normality. This is kind of interesting. It looks like a little ASCII plot that's just showing us where all those points are lying. They're either 0 or 1. And this is just a nicer version of that. Once again, we see everything falling between 0 and 1. So for example, this point here, this non-smoker had a blood pressure of about 164. This one about 161. This smoker here had a blood pressure of about 121. Of these, the regression line doesn't mean much here. What it really is doing is it's just showing you what is more or less the mean of this one and the mean of this one. So as you can tell, see it 140 and 147. So these are just those little things that you really want to sit there and look at them and think about them. Don't just nod your heads like Dr. Ghamsary was saying. So that's our first part. Next, we're going to go ahead and do a couple of regressions. Okay, so in this example, we go ahead and run the general linear models procedure. We check to make sure that everything's there. 32, so we already know all of that. So, and one of the things that I thought I would go over with you guys is just how this proc-GLM works. Okay, so first of all, GLM is, like Dr. Ghamsary said, it's similar to the proc-reg, just has a few more options. It's a cooler approach. But there are some things which proc-reg has that proc-GLM doesn't. So it's not a perfect replacement. The data. Oh, by the way, I called it PSM. He called it 1. I just thought that blood pressure, smoking was just a little more appropriate. I mean, I don't know. The title, the class, here is the variable which you will dummify. I know that's not a word. Anyway, what the class statement does, class, you're going to see it in everywhere in computers, but anyway, here it's defining your classification variable. That means that it's a variable that within its numbers will carry the categories that you're going to define it by, which is what this is. You know, it's only got zeros and ones. Okay, so keep that in mind because you're going to see that in many other places. And whenever we play with Python, you're going to see that there, where we classify our where we use classes in pretty much the same way. So if any of you who have some programming background will just immediately get this. Those of you who didn't, let me go over it once more. Class, like I said, it just looks at this variable and it's going to dummy it. It's going to split it into into whatever values you have. So if you have like that, you have 1 and 0, you have 0, 1, 2, 3. It's going to split it. It's going to treat each one of them not as specifically as numbers, more as classes. And if that's still not getting through to you, just try it a few times and it's going to start to sink in. Okay. Model, of course, is the y equals some function here, you know. In this case, of course, we're going to go ahead and just connect it with the smoking, okay? So we're going to just get one variable. Well, actually, we're not really going to get anything, but I'll show you right now. The solution is what you need to get the results here, okay? You're not going to get anything if you don't go ahead and test this out, okay? Now, the other things, we do the means, okay? And we do the least squares means, these two. The means just gives us the normal means. And the least square means is a type of error reduction means. So we will use them later, okay? As a matter of fact, once we do interactions, we're going to do them even more. So notice, though, we don't really have any difference. And that is because we don't really have any interactions. So we can just kind of ignore that for now. Okay. But let's go ahead and move on to the next one, which is example 2. Okay. So example 2 as you can see, we go ahead and this time though, actually, let me go ahead and show you a difference between these two. So let me just plot 1 and 2 so you'll see the difference. Okay. So we run them. Okay. And we look at that, we look at this. And notice, on example 1, since we're just testing with smoking and non-smoking, all we get is just the mean. This is why our function says just here, says y equals 148 plus 702z. Okay, what is that? Well, that's telling you that when z equals 1, this is just saying y is 1, or I'm sorry, minus 702, which is going to just tell you that it's going to be is 139.98 or something like that. The point is, this value is nothing but a mean. There's no x to it. There's no slope. Okay, because we only have one value. Okay, so because of that, it's only going to give us the closest approximation with just the beta. There's just a beta, and I guess you, Dr. Ghamsary, would call this a beta 1, like that. Now, in example 2, though, we did add a dummy and a continuous variable. The continuous, of course, is age. Okay, and we also added a switch. Okay, and I will explain in just a bit. Okay, now here's what's interesting. Okay, notice that here, okay, our beta is no longer 100 and something like it was here, 148. No, it's gone back down to 48. Now think about that. It took me a while to figure that one out, so see, I told you I'm not that great. But anyway, The reason that you see it go down, the beta is 48 instead of 148, is because once you add age, then age gives you that additional factor. Like I said, it gives you additional freedom to more accurately define the function, and now you have a variable of time that you didn't have before. Before, you only had smoking, non-smoking, so all you can predict is the mean, the beta 0 or the beta 1. Now you have age, and now you can use that other category that we had, which were the numbers here, and now we can actually say, well, you know what? We can now plot it according to age. We included that value. We didn't before, so we couldn't do anything with it. Everything was just thrown in one place. Now that we add it, now it will go. Now when we turn this to 0, okay, when we have the infant non-smoker, this goes to 0 and this goes to 0. The infant non-smoker would have a systolic blood pressure of 4805. It's a nonsense number, but it at least helps us to grasp what's going on there. Okay, but remember, the reason it changed from 140 something to 48 is that we just added that X, and you're going to see it a couple of times. So I just thought I'd share that with you. Okay, so that's one. Okay, another thing is, notice this. Okay, which is, okay, an important thing that you need to always make sure that you do is that you set which one is your reference. If you don't set your reference, okay, right here, what it tells you when you set the reference to that certain value, that means that it's going to turn that value into the default. Okay, if I didn't do it, watch what's going to happen. And let me go ahead and plug this in. First of all, well, let me just pop this window out so you can see it and compare it. And then we will try to run this code again without the ref. And look at this. So what we're looking at, look, that's 48 and 10, okay? So if we don't set this switch here, the one that says ref equals 0, if we set ref equals 0, then it turns the reference into, it looks at the 0 and it becomes the reference, okay? If we don't do it, look at what it did here. Instead, 1 becomes the reference, okay? Remember that the reference is the one that is all 0 and it's the default value, okay? So our value, by the way, the end result is the same. You plug this, you turn this into an equation, it's just going to look different. You know, this one is going to look different than this, but if you plug in whatever numbers, you still get the same value. So if you did that, it just looks weird. Yeah, you didn't break anything. Okay, we'll look at the code a couple of times just to show you that you can play it with it and nothing's going to happen. So that's the cool part of that. Okay. So let's go ahead now and look at the next variation on it. Let's look at example 2b. Here, we're going to do something additional, which is kind of cool, okay? Which is we're going to take advantage of something that SAS can do, which is it's going to center your variable, okay? So, okay, and let's go ahead and compare a couple of things about this, okay? So in this code, okay, we, of course, first we created our data, we read the previous data file, BPSM, and we said CAge equals age minus 53.25. So we're already calling it a centralized age, okay? And we're going to run the proc glm procedure. As a matter of fact, let me show you something just real quick so you'll see. If we do this here, you'll see that, see, we have the CAge there, the centralized age. Okay, so that was just kind of interesting. Anyway, let's get rid of that. Let's run this again. And let's go look at this. Okay, so notice this time our intercept is 139. Okay, our intercept is different than it was before, and we have the age variable inserted. Okay, we have a centralized age variable. Okay, what's going on? Well, when we inserted the centralized age variable, okay, and we told it to calculate the model based on smoking and centralized age, we tell it to solve for this, it will actually calculate it based on that shifting. Remember that this is like a horizontal translation. When you are adding, when you're subtracting 53.25, it's taking that into account. And so it's going to recalculate based on that shift, but nothing else changes. Okay, your C age, okay, and your age, look at this. Your age still has the slope, 1.709. Your C age still has the slope, 1.709. The only thing that you are looking at here, oh, and you're looking at this difference because, once again, remember I said that if I didn't do my baseline here is 1, which it really shouldn't be, but we talked about that. Okay, the most important thing here is this. Your slope doesn't change even though you use age or centralized age. Okay, so hope that explained that kind of interesting curiosity. Okay, now let's go ahead and try example 3. Okay, now this one, okay, it's kind of interesting. Yeah, that was my mistake. Okay. Now notice what we're getting here. Okay, this is what I wanted to show you. Okay, in this code, okay, we're doing something cool. Okay, first of all, we're not reading centralized anymore. We're reading the regular data. Our centralized data, when I do it, we're going to read C BPSM. Regular data is BPSM. Okay, so notice, first of all, our classification variable, I already talked about that, is smoking. We referenced it as 0. That's obvious. Here's what we did that's different. Okay, notice this one says, this one up here, we compare it to 2A, okay, and 3A. Look at these two here. Okay, much of this is the same, okay, except that this one says model equals SBP equals SMK space age slash solution. This one says model SBP equals smoke, the pipe, and then age slash solution. You notice that? The pipe there. That's why I called it regression on one continuous variable with a pipe. Okay. The pipe, by the way, is that key that is above your enter or return and below your delete key on the right-hand side of your keyboard. Okay. So, and in programming, what it does is it sends the output of one thing to the input of something else. You're like, why do I care? Well, that's kind of what's happening here. Okay, you're sending the output of one into the input of another. So what that means is, unlike example 2, okay, where we just treated these variables individually, remember, look, we just treated these as separate entities. In example 3, we're intertwining them. We're not saying, no, they're not separate. These two are married. And we have to see what's going on. What is the interaction? Let's look. Here. Okay. And here. That one took me a while to figure out, too. I was like, oh, my God, why is it? So notice here. Okay. So of these, of course, here's the more important thing also. And there's lots of things. We could also talk about the errors, the fact that the errors change. Okay, but let's go ahead and focus on something more interesting, which is right here. Once we've added this, we have our interaction variable 2. We have our F value. We have the fact that really it's not a significant effect, so we can just toss it. And for the sake of learning, we'll keep it. Okay. remember that our p-value or our f-values tell us that. And later we're going to be playing with the mean squares, so don't forget those. Okay. And here is our, and our sequentials. Anyway, here's the point. Okay. Our intercept doesn't change. We don't expect it to. But notice, here we have intercept, our beta 0, our beta 1, and our beta 2. Okay. Notice here we have beta 0, we have beta 1, our beta 1. Everything is the same, our beta 2. But now we have here. You notice that? We have interaction where this one did not. Example 2, example 3. Example 2, example 3. Interaction. We added that extra variable. How? Simple. We added the big difference between these two is the pipe. One has a pipe there, the other one does not. Okay. The other difference is, like I said, is just because I didn't set the ref equals to 0 right here. If we do, everything looks exactly the same, except for those two differences. Anyway, let's move on. I think you got that point. Let's consider now, we're going to do a regression by dummy and centralized age and interaction. So we're going to go ahead and so we're doing everything again, but now we're doing it with the interaction. Do you notice the pattern we're following here? We try it with a regular variable. Now we're trying it with now we're trying with the centralized variable. Okay. Here, as I said, remember when we centralize, it's just a horizontal translation. So the horizontal translation doesn't change our slope. Look at our slope here. Our slope there and our slope here is just 1.515 or 1.52. The only other thing that we do here is, of course, we add the interaction variable. And we add it exactly the same way we did with the other one, which is our pipe. Notice that? That's all we really did. So if you want to test your variables individually, add them with a space. If you want to test them with an interaction, add the pipe. Now, since we're going to spend a while here, may as well show you guys what this one looks like. I'll pop this out. So that's the one with no interaction, centralized no interaction, and this is centralized with an interaction. Notice? So we can compare these and notice a couple of things. Like I said, our ANOVA table is, of course, changed. Think about why. Okay, that one took me a couple of minutes, but eventually I realized, oh, you're playing with your variables. You got an additional variable. Okay, so we have here our example without interaction where we just have a space. This is our example where we use the pipe. Okay. So I want you to look at that and just notice nothing else really is happening. Our slope remains the same, which our slope should not change. Or no, actually it does. Look at that. Interesting. Okay. So let's move on. Okay, those were all cool, but I don't want to have us sitting here for like 5 hours talking about this. I'm sure you got plenty of things to do. Once we have a function like this, I'll even show you how we can play around with it. Okay. That function is this one right here. Okay, I thought I would show you also how we can get a little more intuition about the variables. What I've done is I've opened up Mathematica. It's a really cool program regarding math. I really like it. But here's the point. I just plugged in this function, as you can tell. Okay, there you go. 139.26, 1031, 152 minus 53.25, 0.43, z x minus 53.25. So you got it. Okay, we enter it to input it. Now, look at this. We go ahead and plug our values here. And let's just say that we want the value of 0 for the years. And we want 0 non-smoker. Right? 5832. Now, let's try this. Let's go for the average. What do you think you're going to get? 53.25 non-smoker. Does that number look familiar? Go back to what we did before, and that should give you an idea. I'm not going to give you everything. If I did, then I would actually be doing you a disservice. Okay. What about y of 53.25 1? Does that number look familiar? What about, now let's just try the last one, variation, y of 0 and 1. Look at those numbers. And this is one of the things that I'm saying. When we turn our variable into 0, okay, so y of x, comma 0, look at what it looks like. We have the 139.26, and then this plus x. So this is just y equals, this is going to, well, let's go ahead and expand it. X, 0. There you go. So this is y equals mx plus b, 1.52, and this is the intercept, and that's the slope. Okay, and let's go ahead and if we do y of x and 1, which is for smokers, notice we got a different slope, and we have a different y-intercept. As a matter of fact, if we plot these, okay, notice what we get. Well, we don't get too much interesting there, but look, first of all, here, at 0, there's our y-intercepts, okay? We have our crossover point here somewhere around 24, 25. Anyway, that's not, but the point is we've got different slopes. This is where we test for this interaction here, right here, this guy here. This value here, okay, this value, this is by how much the slope is being modified. So this is like a 0.43 difference in slope. That's what this is telling you here. 0.43 difference in slope. But what is more important for you guys is 2019, which is greater than 05. So this is telling you, like Dr. Ghamsary said, that the difference in these slopes, even though they look like they're very not parallel, at least as far as statistics goes, they are not significantly unparalleled. We can go ahead and, if we zoom in on, say, 90 to 100, that's kind of what they look like to people. 50 to 100, notice they don't look that bad. It's only if we cross from, like, if we cross from 15 to 30 that we're going to notice that, boom, 20 to 35. Yeah, we see that there. But otherwise, if we looked at other sections of this, so the lower that this value gets, the bigger the difference between these two slopes. And remember what each one of these is just telling us. It's just telling us how this is growing. That's what I just showed you here. As a matter of fact, if you plugged in more values, let's not just plug in that. Let's go ahead and say y of a 33-year-old non-smoker. Their blood pressure should be that. What about a 33-year-old smoker? Notice the pressure? What about a 51-year-old non-smoker? And what about a 51-year-old smoker? What about a 72-year-old smoker and a 72-year-old non-smoker? So do you notice our values? This is where we're going to use the equation. This is actually the coolest part. The graphs and everything just start to give you an intuition. This is and I'm going to show you right now. We're gonna go to something even cooler. But let's move on. Okay. So anyway, you can always stop this video and check it out. I'll give you some of the documents if you can use them. If you have Mathematica or if you have a Raspberry Pi, by the way, cool computer. You guys got to buy it. It's like 25 bucks. Raspberry Pi. You guys, please, let me just, there we go. Raspberry Pi. Raspberry Pi. You guys got to buy one. This thing is dirt cheap. Mathematica, for most people, will cost, for students, cost like about 100 bucks. I think Loma Linda has it. If they do, cool. If they don't, buy a Raspberry Pi. And by the way, installed in Raspberry Pi is Mathematica for free. It's worth it just for that. So, anyway, so let's go ahead now and go to example 4. Okay. Now, this is our first of our race examples. Okay, so, and as you remember, 1 is white, 2 is black, 3 is Hispanic, and 4 is all the others. We're not going to really harp on the philosophy or the other arguments about it here. We're just looking at the numbers. So let's go ahead and worry about that. Okay. So here's our numbers. Here's everything. Okay. And how did we do it? Which is what we're really here to look at. Everything else, look, everything kind of checks out. Okay. We got our, and here's where we actually use these values here. Okay. We will actually prefer to use this value, our least squares. Okay. Now, so what are we doing here? So we're saying proc GLM again, title, class, once again. This time though, notice before we said class smoke, this time we are dummying up the race variable because remember that it's got 4 values, 4, 2, 3, and 1. So it's going to split it into its dummy categories. If you got 4 variables, you're going to have 3 dummy categories. So pretty clear, right? Okay. Our model, once again, our model is our y equals mx plus b. And that's going to be systolic blood pressure equals and then race. Okay. Now, once again, we have no other variables. Okay. So when we pop out our solution, this is why we get y equals 144.80 plus 0.80 this, and you know that if you add a 1 there and 0's there, it gives you 1 value. You add a 1 there, 0's there, it gives you a different. So, okay, so let's go ahead and look at, this is example 4b, because this time now, what we're going to do is we're going to add age and race. So notice what we did here. We still have race as the class, but now we said race and age with a space. So there's no interaction. Okay. We just, our means here and LS means are just to give us some additional a tighter grip on the betas. So we run our solution. All of that you've already seen a couple of times. So we run this code. Okay. Here are our intercept, our race 1, race 2, race 3, and our reference is race 4. If we would have said ref equals 1, then this would have been 0. If we would have said ref equals 2, that would have been 0. So you get that, right? The slope, 166.99.45.84. All of that's pretty clear here. So all we did now is every time we're adding some new twist to the equation, which is really, I agree, Dr. Ghamsary really did a fantastic job of showing us all the variations. I mean, you're not really going to need much more, at least most people, you know. Now, let's go ahead and look at when we actually run it by, instead of age, we run it by centralized age, okay? So, there we go. Okay, and here, okay, once again, we've got, here, let me show you with, oh, yeah, there's the one. Okay, so once again, we get our values, we get our centralized age, and remember that every time, again, I'm going to repeat it because I had a hard time getting it. Whenever we have a centralized age value, our intercept will shift, okay? And that's why it's no longer in the 50s. This intercept is either going to be high, either because we didn't even include age, so everybody's just dropped into some average category, or when we include a centralized age that gives us a horizontal translation, okay? So, okay, now we're going to go to the next one, which is this one. We're going to do a regression with interaction with race and age. So the same thing as we did in 4C, except now we're going to pipe it, okay? So we go ahead and okay, notice there's the only difference here is that we piped it. So I will show you, as a matter of fact, I'll run them separately just so you'll see. So here's this one. That's the variables by themselves. And then here's the variables interacting. So you notice every time we add the pipe, all it really does is it just makes our variables, it just adds our interaction variable. There we go. Notice? So we had beta 0, beta 1, beta 2, beta 3, and beta 4. But here, because we have interaction, it's going to interact with each one of them. So it's going to be beta 0, beta 1, beta 2, beta 3, and beta 4. But then we have beta 5, beta 6, beta 7, and beta 8. Well, no, there's no beta 8. And of course here, we would normally look at these values. Okay, I'll leave that for you to figure that one out. But notice some of these are not really that useful. Okay, that's what Dr. Ghamsary was saying. Now, let's go to the last one, the most interesting one in my opinion, which is 4E. Okay. And this one, we just throw everything but the kitchen sink. So let's go ahead and have a little bit of time looking at this. Okay, so here, remember, because we are piping it through central, well, actually, it's the same thing. I'm sorry. Just we're using centralized age. Okay, so we have again our race and age interactors. Okay, and this time we have our centralized age. And remember what I said, whenever we have centralized age, it's just a horizontal translation, which is why our intercept has this different value. As a matter of fact, this is where we move on to the other cool manipulation, mathematical manipulation. Okay, so everything else I think you get. So let's move on to the next one. Okay. So in this case, okay, here's the equation, by the way. Let me go ahead and show you. Okay, this is y equals 141, 85, 243. That's just torture writing down, which is why Mathematica is my friend. Honestly, though, if you can't write this stuff on pencil and paper, you probably shouldn't be using Mathematica anyway. So here we go. So this whole equation is there, so we enter it. Okay, now let's go ahead and try a few values. Okay, so let's go ahead and say what is the value of y of a baby. Okay, and then let's go ahead and set 1 who is white. 8191. What about a baby who is black? That'll be 212. What about a baby who is Hispanic? What about an infant who is all other races? Our beta value, 5655. By the way, did you notice something cool? Look at this. This value is not that one, which is why when Dr. Ghamsary asks you, what is 141.85? It is not the value of an infant non-smoker, because you have to account for the fact that, look, this turns to 0, but you still got values here. 160 minus 5325. So you've still got a value that's going to reduce it. This one. It's not exactly 141.85. There's a difference there. That's why you want to play with these equations, okay? So we can try other things. Oh, by the way, you might be like, wait a minute. Why does a black baby have a blood pressure that's so much lower? When perhaps some of you who are in public health might be like, well, usually African Americans have more problems with hypertension. Because, like Dr. Ghamsary said, this equation at 0 is really meaningless in real life. As a matter of fact, remember one thing, okay? Our data here, okay, our age is in the 40s, 50s, and 60s, okay? You will almost never run your regression equation outside of the range that you tested it inside of. If you did, you got to use some really crazy math to prove, because the further out you get, the less accurate. That's why at 0, this is like this is nonsense, okay? It's just there because it helped. Because actually, let's do this. Watch. Let's just say of a 65-year-old white person, and let's go ahead and just set the other ones. 65-year-old black person. Oh, sorry. These can only be 1s and 0s. And then of a 65-year-old Hispanic person, and of a 65-year-old anybody else. And notice, at 65, the white person is 152, the black person is 161. As a baby, they were lower. Well, yeah, we're going to notice in just a bit why. But notice, a Hispanic person's even higher. Oh, that's 170. Wow, that's pretty bad. So, we've got a lot of so there's a lot you can think about. I just wanted to show you the mathematical intuition, though, as you're plugging in numbers. Like I said, we can go ahead and do the same thing at any age. I mean, we can go ahead and plug in, 75 and compare them. But as you notice, so plugging in the numbers already gives us some values. And that's what the regression is supposed to do. It's supposed to give us some predictions. So that if you talk to somebody, oh, I'm 75 and I'm Hispanic, then this should tell you, well, this is what your blood pressure probably would be. Ugh. I would almost suggest LASIK or something like that, but honestly, I have problems with that. But I'm not a doctor, so I won't talk about that. Okay, so the last part is we're going to go ahead and play with this just a little more. Okay, so I'm going to show you. This is the full function, and we go ahead and plot it. Okay, so let's just get an idea of what's going on here. Okay. In this case, this is what you were looking at, okay? Which is you were looking at the white person whose blood pressure begins higher, but the slope is what really matters. Look, that slope is the lowest, okay? The black person began lower, but the slope is higher, okay? But look at the Hispanic person. Look at this slope. As a matter of fact, there it is. That's a 1.8 slope. That's a 1.99 slope. So that slope is a 1.08 slope. That's barely above 1. You know, it's almost like a 45-degree line. 1.99, 1.6. So the all others are about 1.6. Okay. So there's a lot more we can look at here. So we can also close the range down. We can look at the interesting area from our, like I said, our values were what, between 40 and 70? Well, why don't we just run a product means on it? So our age varies from 41 to 65. That's where we can actually make our predictions. So let's do it. Let's do it 40 to 66. This is our range that we measured our variables. If I had time, I would have dropped a scatter plot in here, but here's the point. What we're looking at here is really where these lines are their most useful. Anybody that is within these age ranges, these lines, in theory, should be quite close to predicting. So you run into a white person at 60, and that's roughly going to be their value. Like I said, you know, any person, you run into a Hispanic person, and like I said, it's pretty high. Wow. Wow, that scares me. I hope I don't go that high. Anyway, so I hope this gave you at least a little intuition. If any of you likes to run Mathematica code, or if you have Mathematica available, let me know. I will share this with you so that you can play with it a little. Okay. I will also try to save the SAS code, although I think Dr. Ghamsary already has it. I did a few small modifications, nothing significant. So if there's anything else, let me know. But hopefully that gave you at least a slightly different perspective. Once again, I'm sure I made some mistakes, and as soon as Dr. Ghamsary or somebody else tells me, not just him, anybody else, I will do my best to correct him as soon as possible. Okay? Just another student sharing his observations. Hope they helped a few of you. And until next time, take care.